0 to stage 1, the element will save the previous reaction and will apply them as external forces. So this is one point. But the boundary traction is something different. The boundary traction here are basically basically what I do inside is first I compute the stresses in my free field. Okay, then I take the shear stress and the horizontal stress. Okay, I project it onto the vertical side in such a way that I have the boundary tractions on this side. I take them and I apply them as external forces onto these two nodes. Okay, this one, pay one attention because this one produces a non-symmetric matrix. Okay, because in this case the force is transferred from the free field to the solid domain, but not on the other side. So this one produces a non-symmetric matrix. And this one was the component that was not available in the previous version of OpenSees. Okay, that's why sometimes you have seen some strange displacement at the solid domain, because actually this traction was missing. So the information in the free field was not transferred to the solid domain. Okay, so but at the end of the day, what it does, takes the stresses into the free field, converts them into boundary tractions. Okay, just by projecting a stress tensor onto a plane, you obtain a traction vector, and this traction vector, well, is lumped with the length of the element, and it is applied onto the solid domain nodes. But it is done at each step, but actually at each iteration, because it is inside the element. Okay, so the solution is correct in this case. Okay, therefore this allows to reduce drastically discretization, right? Yes, but as you will see in our example, the discretization is actually governed by few other things. I will show you later on. So basically by the frequency of the input motion that you have and the shear wave velocity of the soil. Okay, what it allows you to do actually with respect to the previous implementation was that, well, actually it is more accurate, so you don't have disturbance of the boundaries, and you can use a larger time step, because in the not in the, well, actually I didn't do it, but if you use the equal code in the previous version, okay, where you didn't have the transfer of boundary traction, you could have simulated something like that with a equal code, but doing that it's like doing it explicitly, so you need a small time step. In this case, you can use a standard time step for implicit schemes. Okay, but actually the mesh size is constrained by something else, and I will show you later on. Okay, so the first difference, the first thing that you have to pay attention to is the boundary type. For 2D is quite easy. For 3D is much more complicated. Okay, so doing it manually in OpenSees can be quite challenging, but if you are good at programming, you can do it. Okay, so this is the second note. Then you have a third note which says the element works in two stages. Okay, the first stage, which is the default one, so when you create the element is in stage 0. So in the first stage, the element acts as a fixed condition suitable for the first gravity analysis. It stores the reaction and automatically converts them into applied boundary forces when switching from stage 0 to stage 1. Okay, then when we switch to stage 1, the element does not act anymore as a constraint. Okay, but it applies the equivalent reaction forces. And in stage 1, instead, it is converted into the real absorbing element. So the element that I show here. Okay. Oh, let me go back here. Okay, so it acts as an absorbing element, and the reaction of the previous constraint element are applied as external forces. Now, the conversion from stage 0 to stage 1 can be done using the either the set parameter command or the parameter and update parameter command. Okay, there are two ways of doing it. Okay, and then everything is summarized into the example. And now there is a warning about the mesh discretization. Okay, actually about the distortion. Now this element actually, if I zoom a little bit here, you will see that due to the way you construct this element will always be perfect in the extrusion direction, okay? Because actually you take the layer of faces at the boundary, you extrude them, okay? So in the extrusion direction, it will always have zero distortion, okay? But if for some reason, okay, you need to create some cuts here along the height, because probably you have different material layers which are not parallel to the XY plane. What happens is that in the X, Z, or in the YZ plane, you may have a mesh distortion, okay? This mesh distortion will create some perturbance onto the solution. It's not that bad. In fact, here, actually, you need to zoom a lot to visualize the error here. It's not that bad, but pay attention that if you can use a non-distorted mesh, the solution is exact. If you use a distorted mesh, you may see some perturbation in the response, okay? So this is a warning. And then here I have an example for people doing this kind of simulation directly in OpenSees, okay? Now, very briefly, what this example does is to create the 2D version of this example, basically, okay? A simple 2D version. Here I created the material properties, all this stuff. Then I created a simple loop to create the nodes, a simple loop to create the elements, and to identify the boundary element. Now in 2D, it's pretty easy to do it manually, but trust me, if you try to do it in 3D, it will be very challenging. Okay, then you do the first analysis. When you're done with the first analysis, you call the set parameter command. The parameter that you want to update is the stage parameter, and you want to update it to a value of 1, because as I said, when you construct this element, stage is equal to 0. You do the first analysis, it is acting as a constraint. Then you switch the stage parameter to all the absorbing elements from 0 to 1. And now in this case, you can run the dynamic analysis, okay? Now, through the script, this is quite complicated to understand how it works. So I will show you now how it works in SDKO. Okay, so I think this is pretty clear. You just need to pay attention. Oh, in this example, you will see how, well, this is a benchmark, okay? So instead of applying a real earthquake, I applied a Richter wavelet with a certain frequency, okay? And the output will be the acceleration recorded at the bottom of the soil model and at the top, okay? At the soil base, so at the bottom, the solution will be an acceleration which has the form of a Richter wavelet, whose peak is equal to 1g, okay? Then here is when the wave enters the domain, okay, from the bottom. Then it travels, it hits the free surface on the top, okay? And here what you should see is actually the same shape, so a Richter wavelet, but with twice the same acceleration, because I didn't use any Rayleigh damping, so there is no damping. And because when the acceleration hits the free surface, you will read twice that acceleration, okay? Because you don't have the other half space that balances half of the acceleration. So you will see G here, 2G here, and then the wave travels back to the bottom. That's why you will see a second wave here on the soil base, and then you will see nothing because you have absorption, okay? You have all the waves are absorbed, okay? And now you will see this one very clearly in the SDKO example. So what I want to do now is to go in SDKO, close this one for a while. Now, if you remember last time, what you will see by Monday on this webinar will be the soil foundation structure interaction and the 2D example. In this 2D example, I will show you how to take the 2D example that for which I gave you a preview in the previous webinar. And if you remember, I created those elements manually, okay? So I created the left boundary, right boundary, and the bottom. But now in the version 2.0.5, we made an automation which makes it even much easier. And I will show you how to convert to the new version, okay? So for example, I go here, I open what you can find in the previous webinar, the webinar about contact, which is this one. If you remember, there was not only the contact examples, there were some examples for the absorbing element, just as a preview. Okay, so I will show you how to convert just one of them, the easiest one. So the 2D case, which is actually the same as this example here. So I open this one. It will be updated to the new version automatically, and then I save as. I go here to the 2 days webinar, to the example, okay, and save. Okay, so I will start with the previous one. Now, as you can see here, what I've done as a first implementation was to exactly follow the steps that I created here in the manual. So I'm doing a 2D analysis. Oops. I'm doing a 2D analysis, so I need the soil domain, and I need also to model the boundaries, okay? Now this one was quite tedious, not much in the 2D case, but for sure much more in the 3D case. Oops, I run another instance of SDKO. Let me close it. Okay, so what I've done was to create a surface here. Let me go in property. The inner surface, the purple surface here, was the soil domain. Then I manually extruded the boundaries of the soil domain to create the layer of absorbing elements, okay? Then in the physical properties, I had a simple elastic isotropic model for the soil domain. And then I created an ASD absorbing boundary 2D material, okay, which has the same G and Poisson ratio and same rho and same thickness of the soil domain, okay. Then I created one standard element, one standard quad element in plane strain for the soil domain, and a combination of actually 5 combinations of absorbing elements. Why? Because in the previous version, the absorbing element was here under absorbing boundaries, and you had ASD absorbing boundary 2D or ASD absorbing boundary 3D. Okay. Now in the new version, by Monday, you will find also ASD absorbing boundary 2D auto and ASD absorbing boundary 3D auto. This one stands for the automatic version of the manual ones. Now, basically, in the manual one, you needed to explicitly tell STKO what kind of boundary it is. So it can be bottom, left, right, bottom left, or bottom right. Okay. Now in 2D, it's not that difficult because you have at most 5 combinations. But trust me that in 3D is much more complicated because you have 17 combinations. Okay, so it can be quite challenging, and also error prone because you need to extrude all of them. Assign the correct boundary. For some reason, you assign the right boundary, for example, to the left side, you will have an erroneous result. Okay. So what I decided to do is to create a much easier approach. Okay. So I will show you how to convert this one into the new version. Okay. So the first thing, I'm going into sub-selection, and I will remove all the boundaries because now in the new automation, STKO will automatically extrude the boundaries, okay, while computing the OpenSees solution. So I remove this one. In the new version, all you need to do is to model the soil domain, okay? Then the material is fine. The material is the same, okay? In fact, if you go in physical properties and you go in material, ND, absorbing boundaries, there is no difference, okay? The 2D and 3D material are the same. But now they should be assigned directly to the boundary of the soil domain, okay? So I select the left edge, bottom edge. Let me go in geometry, otherwise you don't see it, okay? Left edge, bottom edge, and right edge. And you can drag and drop the absorbing boundary material. And you also need just one element this time because, why? This automation, basically, since it is an element applied directly to the boundary of the soil domain, I can directly compute the outward normal vector. So STKO is able to understand whether it is on the left, on the right, on the bottom, or on the corners. Okay, so it's much easier. So I go here, I just write boundary, and I change it from the manual one to the automatic one. As you can see, it is the same. You don't have to specify the boundary because it is automatically computed by STKO. You just need to specify what is the base action. Okay, now in this case, I want just to apply a Richter wavelet of 10 Hertz in the X direction. Okay, then if you want, you can also apply it in the vertical direction. Okay, now I can simply select the same edges I used for the material, and I can drag and drop the element. Okay, so much easier. So you have the material, you have the element. The forces are applied only on the soil domain. Here you can even simplify this one, because if you remember, I had to create a set of absorbing elements because you need a selection set to create the update parameter, to create the parameter and the update parameter. As you remember, I used the standard approach of creating a parameter. The parameter should have the type element, the name of the parameter to update, and the selection set that you want to update. Now, this is not possible, of course, because the element has not been created here at this point. Okay, so the element will be generated automatically by STKO. So how do you update a parameter for an element that is not in STKO? Actually, it's much easier. So you don't even need this one. Delete. You don't need the parameter and update parameter. You just need one automation that we created in the new version, which is here. You can go in miscellaneous command, absorbing boundary, ASDabsorbingBoundary activate. And this one is the same for 2D and 3D. It has no parameters. Okay, you just create this miscellaneous command and you place it here between the gravity analysis and the dynamic analysis. And this one does exactly what the combination of update of parameter and update parameter was doing before. Okay, but it's much easier because you don't even have to care about what is the selection set of the absorbing boundary. It is just a single command. Okay, so much easier. You don't need to create anything for the absorbing layer. Now I just want to change slightly the. Oh, we have a question. For the 3D case, the element and material are assigned to surfaces, right? Yes. Then STKO takes care of the corner element automatically. Yes. If you want to know how, you can access the source code of the element. It will be that you will see that it is quite complicated, but we managed to do it. Okay. But now you will see how STKO creates these elements. Okay, so you have the update parameter here. I just want to change because now I deleted the absorbing boundary, so I need to set up the selection set that I want to monitor. So this one will be just the bottom. It doesn't have anything, if I remember. Select, okay, it doesn't have anything. So here I want to use this node to monitor the solution at the bottom. So basically what I want to obtain now is the blue graph. Okay, I want to monitor the wave entering the soil domain and exiting the soil domain. So I need a selection set here, add to selection set. And in this case, I want the top instead. I want to monitor what's going on the top. Remove from selection set. And I want to use this one. Add to selection set. Okay. So this one is the bottom node. This one is the top node. This monitor here will be bottom. It is monitoring the acceleration versus time, acceleration in the x direction of the bottom node. And this one will monitor the acceleration at the top. Okay, so top, always acceleration in the x direction. And then you have the dynamic analysis. Okay, now in this analysis, I didn't use any damping because I just want to see a benchmark. Okay, so I want to see that at the base, I have the an acceleration of 1g entering the system. Then I want to see the same acceleration, but with twice the magnitude at the free surface, because this is what happens if you have a single material and you don't have any damping. And then I want to see the same waves that hits back the bottom and gets absorbed. Now, of course, if you place some damping, you will see that the values will decrease during the analysis. Okay, so you have everything. Now, the next thing that you need to do is to mesh it. Now, one thing that I want to show you is that here I already used a proper mesh, but in the same folder, to the example, you will see a support file, which is a duplicate of the support file you will see for the soil interaction model, where you can do some computation. Now, in this case, my material model has 3 to the power of 9 as a Young modulus, 0.3 as Poisson ratio, and 2100 as mass ratio. Okay, so you put them here, and you will have the shear wave velocity, the maximum frequency of the input motion. Now, the Ricker wavelet I put there as a frequency of 10. So if you want to compute the wavelength, it is the shear wave velocity divided by maximum frequency. Now, the typical formula is to take the wavelength and divide it by 8, so that you have at least 8 elements per wavelength. Now, actually, what I've seen is that for the Ricker wavelet, this kind of mesh is too large. You will see that. For example, here, my mesh can be at most 9 meters. Okay, so let's see what happens if I use 9 meters. I'm going mesh. Here I have a global seed of 10. Okay, because now I'm only interested in how the wave travels vertically. Okay, so I can use any dimension here in the horizontal direction. So the global seed is uniform by size, and it was 10, as you can see here. Okay. Now let's apply an edge seed here at the sides, which is 9 as given by the equation assigned. So it's pretty much not uniform by division, but uniform by size, sorry. So I put 9 here, assign, done, and build the mesh. Okay, so it's quite square. You will see that this mesh will not give us a correct result. Let's see. I'll plot all the minors. Okay, so here you will see some disturbance. Okay, but already here you will see that there is an error. Okay, let's see why. Actually, it's not a problem of absorbing the element. The problem is due to the mesh size, because here, right at the beginning, you will see that I should have 9.806, but I have more than 10. So why is this happening? Let's go to the post processor. Then I will show you the larger example. Now, if I go here in the 2D example we've just done, okay, now, first of all, as you can see, this is the extra layer of absorbing elements, okay? It is being automatically created by SDKO, okay? So right, left, bottom, and also the corner, okay? So this is the first interesting thing, is that the absorbing boundary are created automatically. Now, let's see how they look like. So first, in the first analysis, let's see the displacement field, okay? So you have a vertical displacement. Well, here is moving not that much. Oh, well, of course, it was at the beginning. Let me go to the end of the first stage. Okay, so this one is the vertical displacement at the end of the first stage. And here you can see, for example, if I try to visualize the reaction forces, you will see that the reaction forces are automatically computed by this element, okay? Of course, you will see the reaction only at the interface between the absorbing boundary and the soil domain, okay? So this one are the reaction. It's even easier if you visualize them using the vector plot. We go at the stage 1. And here, and we try to visualize the reaction forces, okay? So here you have the reaction forces computed by the absorbing element. And this is also very, very nice, because when you create this kind of element, as you can see, you don't have any constraint. you can see here, because these elements act as a constraint in the first stage, okay? And then these reaction forces remains also during the dynamic analysis. Now pay attention, for those of you who are not aware of this one may seem strange. Why is this happening? Because when you do a dynamic analysis and you want to see the static reaction, you need to ask for reaction forces including inertia, okay? Otherwise you see the inertia forces as a reaction, okay? So when you are doing dynamic analysis and you want to see only the reaction, only the reaction at the constraint, you need to ask for reaction forces including inertia. Otherwise, if you ask only for reaction forces, you see also inertia forces, okay? Okay, so this one is just to explain the reactions, but let's see why the solution was not correct in the dynamic case, in the dynamic stage here. Let me use also the acceleration as displacement. Okay, so this one is when the wave is entering. As you can see, yes, the wavelength of the entire Richter wavelet is, it was, let me see, 74 meters. So it means more or less 8 elements. But actually is 8 elements from here to here. But in this case, for a Richter wavelet, you need to consider a smaller wavelength, okay? So you can visualize it manually, visually here. So basically, the first thing that you have to pay attention to is to use a correct estimation of the mesh size, because if the mesh is too large, then you have some either increase or decrease in the acceleration field, okay? And the solution will not be correct. And also, when it hits the surface, it goes back. But as you can see, you have many reflections here because one element is reflecting against the other, okay? So the element is too large for the kind of for the acceleration field. So basically, at the end of the day, here what I found is that I need to use 1/10 of this equation. Okay, so this equation says that you need to have 8 elements per wavelength, but at least in the Richter wavelet, it seems not to work. So I need to divide it by 10. Okay, so let's try to do it manually. Let's first, instead of 8, let me use, I don't know, 4.5, so 1/2. And let's see if the solution improves. We'll mesh and run it again. Now it seems better. It's not perfect because, as you can see here, it's still too high. It's 10, while it should be 9.8. And also here you see some non-symmetry and of course some reflections, but those reflections are not due to the absorbing boundary, but are due to the fact that if the element is too large, it reflects the wave with the neighboring elements, okay? So it's a discretization error. So basically what I've done is I kept decreasing the mesh size, and I found that the proper mesh size for this problem was 1 actually. So 1/10 of the proposed of the typical wave critical mesh size. So uniform by size, 1, done, build mesh, and run the analysis again. Now it is fine. So if you look here, it is approximately 9.8, so 1G. Oops. Yeah, there's a little bit of lag, so let me wait for the entire analysis to finish. Let me open again. Okay, now it is good. And here you have 9.81. Okay, so this is fine. And here you have twice that value, okay, because it is hitting the free surface. So this is exactly what we want to see. At the base, we have the wave entering, and then the same wave that is hitting back the surface, and it is absorbed, okay? Which is basically this output here. So let me restrict the result between 0 and 9.806. Let's go back to the beginning, and you will see the wave that enters. Okay, now the discretization is fine. As you can see, you need many elements between the wavelength to have a benchmark solution. Okay, now most of the time this is not feasible, so you use a larger mesh. But in this case, I want to show you how to obtain a proper mesh. Okay, so this one, when the wave is entering, is the first part of the graph. Then the bottom is free from accelerations, which is this stage here. Now the main wave here is hitting the surface, okay? And if I remove this constraint here, you will see that it is actually twice the same value, because it was 9.8 until it was inside the soil domain, but when it hits the free surface, it becomes twice, the magnitude doubles, okay, because it is a free surface. Then it goes back, and we put once again the limit, and it is absorbed at the bottom, okay. And then from then on, you don't see any other diffraction, okay. Now, of course, if I remove these two, you will see some waves, but actually are approximately 0, okay. It is just some numerical error, okay. But as you can see, it is not moving anymore. It's just something like 1 to the -4, -6, okay. And this is actually the solution that you want to obtain. Okay, so in this way, we have validated this element, okay. For the 3D case, it's the same thing, okay. I will show you how to do it now in the soil interaction model, but you may imagine that the procedure is the same. So you need the update parameter, which is the same. The material is the same, but 3D, and the element is just one and should be applied to the boundary faces, okay. And then a STKO takes care of doing the extrusion. Well, this one is fine. Save. So now you know how to convert all of them. So basically, as an exercise, you can go into the folder of the previous webinar, which was the webinar of contact element. You can go here in absorbing, and you try to convert all of them. Okay. So the first two are 2D, and then you have 3 examples in 3D, and you will see that it is very easy to convert them into the new with the new automation, okay. Of course, by Monday, because you need the new version of STKO. Okay, now the other example that I wanted to show you was actually the same soil foundation structure interaction model that we have done in the previous webinar, but it was just a static analysis, a pushover analysis with a small piece of volume, which was fixed. Now, what happens if I want to do a dynamic analysis of this one? Now, actually, I didn't have time to run the entire analysis because it takes a lot. You will see that the mesh size constraint is very demanding. So I have only the initial stage of the analysis. Then I will finish to run it during the weekend, and by Monday I will update also the solution of this one. Now let's try to have a look at what this example is. So here you will see in soil foundation structure interaction model this kind of model here. Now, if you remember last time, I only did this model. Actually, this one was not available. Let me hide it. You only had this kind of model. Okay, so you had a small piece of soil here. Then you had the foundation. In the middle, you also have the piles. Okay, so this one, it was the same model that I used last time, but with fixity boundary condition at the sides. Okay, now what I tried to do in this example was to create a layer. Let me show everything. Okay, enlarge the domain. Okay, because I want to apply the same Ricker wavelet at the bottom of the soil and see how it propagates what happens when it hits the free surface when there is the surface, and what happens when the waves goes back. Now in the same folder, you will find, well, the same of this file actually, but where it is here, with the material parameters for the for this model. Let me show you a little bit all the contents here. So here I was modeling everything in Newton and meters. So I was using the International Unit System. Here you have the soil data. So material parameters for the soil data, the computation of the S and P wave velocities, and the computation of the maximum frequency given by the standard equation. But as I told you, I should use this one divided by 10, actually. So the mesh size will be quite demanding. You will see that the solution using this one is not correct, okay? And that's why I didn't have time to run the entire analysis, but by Monday you will see that. Then I have also the material parameters of the pile, okay? So material parameters, the diameter of the pile, the area, and then the self-weight per unit length and mass per unit length that you should assign to the beam, okay? Which are actually here, for example, for the pile. Where is it? Here, pile property, no, element property. For the pile, you have the mass here, and same thing for the self-weight, okay? So all the computation that I've done here is reported into this Excel spreadsheet. Then for the structure, the entire structure is made with the same cross-section just to speed up the modeling. So same material parameters for all the beams and all the columns, same section. Okay, these are the sides of the section. This is the area, and once again, the self-weight and mass per unit length. Then you have the properties for the foundation. It's a slab with a 0.5 meters thickness. Now, in this case, the self-weight should be a pressure, so a self-weight per unit area. Basically, the self-weight multiplied by the thickness. And then you have some data for the contact. Okay. Now, for all the contact, what I've done to estimate the normal and tangential friction, the tangential coefficient for the penalty, was actually, for example, for normal contact, I took 10 to the power of round. This one actually is in Italian, but it means round, log 10 of what? Of the Young modulus of the normal stiffness of my soil domain, which is the Young modulus of the soil domain times the characteristic length of the mesh. Now the mesh in the inner domain here is actually 1 meter, okay, which is this one. And I took this one, the order of magnitude, because the log 10 of this number gives me the order of magnitude of that stiffness, and I add 1, okay, just to have it 10 times stiffer than the material model. While for the tangential stiffness is different, I already told it in the previous webinar. I took the shear modulus of the soil, but typically the shear modulus of the interface is not that of the soil, okay? So it depends on the asperity. There are many papers explaining how to calibrate these parameters, but typically it is a fraction of the shear modulus of the soil. Now in this case, I took 1/10. Same thing for the friction angle, okay? Sometimes it is less than the friction angle of the pure soil. Okay, see here you have all the data. In the second spreadsheet, you have a way to calculate the Richter wavelet, but in terms of velocity, because you need the velocity, not the accelerogram, you need the velocity here. So you put the frequency here, you put the entire duration, and well, you need the duration actually because the equation I have for the Richter wavelet is centered at 0. Okay, but of course I want to center it here in the middle of my analysis. So if I know that my entire wavelet lasts 0.25 seconds, here I do an offset. Okay, so basically you can just copy paste these values into a time series path, which is up here. And you have a Richter wavelet velocity field, okay? Okay, now I want to explain you how I created this model, okay? Now I'll give you a brief summary and then I will try to build it from zero, Okay, so starting from the main model, here I wanted to use a mesh size of 1, okay, because I needed a fine mesh under my under the structure, okay. But then to save some time, even though it will not produce a correct result, but I want to save some time, so I decided to create a soil domain, a surrounding domain, which has a coarser mesh and also less details. Okay, as you can see, the geometries are not compatible. How can you join two non-compatible meshes? You can use the where it is, the embedded node element. If you remember, I also gave a webinar. It was not the previous webinar, it was the other one, talking about how to embed rebars inside soils, inside solid domains. But actually, you can use the same constraint to attach two incompatible meshes, okay? And I will show you how I realized this one. So in this way, basically, I'm able to have two different meshes connected with a kinematic constraint here at the boundaries without creating any mesh transition, okay? And then I will apply the absorbing boundaries at the sides of this soil, okay? Why do I need this one, which is so large? Because as I told you, the Ricker wavelet that I want to apply has a total wavelength of 61 meters, okay? So actually, the detailed soil here is only 15 meters, okay? That's why I need a soil depth which is at least larger than the total wavelength, because I need the wave needs to enter, needs to completely exit the input. It should hit the free surface and goes back, okay? So if I do a model which is less than the total wavelength, okay, you will see some reflection because the wave will be reflected from the top while there is still an acceleration entering the system from the bottom, okay? So you will see some reflection in that case. So that's why I needed such a huge soil model. Okay, so let's try to see if I can do it in 15 minutes from now. And then, of course, you will have the entire model already done, okay? So let me remove this. And also, well, I leave here the absorbing boundary. I will assign them later on. The transition, okay, is the boundary condition. Okay, so let me create now. You start from this one. What I did was to remove. So this one is the same model I've used in the previous webinar. I just removed the fixities at the boundary. As you can see now, here I only have kinematic constraint for the master nodes of the structure, of course, because the master nodes should be fixed in the out of plane direction, the rigid diaphragm, but then you have only forces. And finally, you will need this kind of constraint to attach the coarse mesh to the fine mesh. But this is not mandatory because if you have enough computer power, you can use the same discretization in the entire soil, okay? So you don't need this transition. This is just a way to show you how, if you want, you can create a let's say a multi-scale model where you have a detailed model and a coarser model. Okay, so let's say I want to create a soil domain, which is at least 200 meters per side, okay? So if I switch on this one, and this one is 100 meter, okay? So I would like to create a soil domain which is at least this large. Okay, so I create first a square here, which is on the same plane of the top free surface. Okay, then I need to create a hole, okay, to place this detailed model. Okay, so for this reason, I need to create some cut lines. And here I need the orthogonal constraint. Also here. Now I move them backward in such a way that it intersects both edges, and then I do the same on the other side. Now, the nice thing about creating these two separated domains and then attach them using this kind of transition is also because, well, first because you can connect different mesh resolutions, but also because sometimes here, due to the presence of the pile, as you can see, the soil domain is quite complicated, and if you want to enlarge it, you need to propagate this mesh down to the bottom. Well, actually, this is not necessary for the resolution at the bottom of the soil domain, okay? So if you want to simplify the model, you can just create a hole here, you create a soil, and you embed the detailed model inside the coarser model. So I move these ones backward, okay? This one should be a little bit more here. Okay, now I can do a merge of all these construction lines. And now that I created a merge, I can remove these exceeding edges. Delete. Okay. Now I can get rid of, oh, I just need to measure what is the total height of my detailed soil, because then I will hide it. So I go to query geometry, go to properties, and I select the first edge and the second edge, and total length is 15 meters, okay? So now let me hide all these geometries, select, and select, hide, so that now I can work, also the interactions. Okay, so that now I can work only on my new model. Okay, so I have my construction lines. I can create planar faces from surfaces from planar faces, and now I can delete the construction line. Okay, so what I have now is just a planar face here. Now I want to extrude them of what? Well, first I need 15 meters here, so I type 15, press enter, in such a way that I first do an extrusion of the first 15 meters to create the hole, okay, and then extrude the remaining, which is something like this, okay. So I have a 200 times 200 times 200 soil domain. Now that I created this extrusion path, now that I have this extrusion path, I can simply use the sweep command. I select the entire face, right click, and then I select the spine shape, which is the extrusion path. And I can select this one. We have some microphone. Okay, sorry, we had to switch off the microphone. Okay, and extrude along this path. Okay, now I can get rid of the generating surface and also of the extrusion path. So what I have now is this whip here, which is my extended soil domain. And I need to get rid of these central volumes. So I go in sub-selection, I select the solid here and delete, okay? Now basically I have the surrounding domain where I can fit my model, okay? If I show everything, my model is exactly here. Okay, now I want to switch off the grid. Okay, now before creating the transition, I need to assign the elements. So if I go in property, you will see that now here I don't have any physical or element property. So I can go here in sweep, select all the soils, and I drag and drop the soil material, which is actually the initial state wrapper, because if you recall, I decided to use here the initial state wrapper for the first analysis. So drag and drop, which is basically the same material I was using here. And for the element property, I need to use the same material, the same element, sorry, of the soil domain. So once again, I select all the soils, all the solids of the surrounding solid domain, and I drag and drop the soil element. One extra thing that I need to do is to assign the same, where is it? Well, I need to do a couple of things. Here I had a selection set, soil domain, okay, because this is a construction stage analysis. So this selection set was used to create the soil domain. Now the soil domain is not only this one, but it contains also all the other solids of this whip solid. Okay, so right click, select all the solids here, and we go into the soil domain and add to selection set. Okay, in such a way that now soil domain contains everything. Okay, well, actually it contains everything, but the holes. Okay, because the holes here are inside the whole domain. Okay, so switch it off, select, show, and here you have the domain for the hole. Okay, if you remember, this is necessary for doing excavation analysis. Okay, so here we have all the elements. So physical properties are fine, element properties are fine. The soil domain has been updated. I need to update also the boundary condition, because if I go in condition here, I have the vertical forces for the self weight of the soil only on the inner domain. So I need to update also the self weight of the soil. So this one, right click. As you can see now, it is applied only, it was applied only on the detailed soil. Now I go here, right click, select, and OK. And now the condition is applied also to the surrounding element. And now I think we have everything. Well, we need to create the absorbing material, okay? And as you can see in the 3D case, it's also very easy. The 3D material is the same, okay, with the same G and Poisson ratio and mass density of the soil material. We just need to create one element, which has the base acceleration in X or Y or Z or all of them. Well, in this case, I only apply the acceleration in X. Now, what I need to do is to select the boundary faces. Okay, so I go to sub-selection, faces only, and I do something like this. Okay, so very easy. I probably didn't select this one. Okay, so I have all the boundary faces and also the bottom one, bottom face. So as you can see here, I have all the boundary faces of my soil, well, except of the free field, the free soil on the top. And I drag and drop the absorbing material, select again, and I drag and drop the absorbing element. Okay. Now I have all the absorbing element set up. The only thing that is missing is the connection between the detailed model and the surrounding soil, because now my model will be singular because the inner domain is completely detached from the outer domain. Okay. Now I need a way to connect them. Now, due to the incompatibility of the mesh, but also of the geometry, I need another way to connect them. And this one can be done through this transition constraint, which is the embedded node element. Okay, how can you do this? Well, first you need an interaction, okay, a new interaction. This interaction should be a node to element, where the master is the element and should be all the soil, all the solids, the surrounding solids, because it is the coarser mesh, and the coarser mesh typically is the master in a kinematic constraint. While the slave should be the nodes on the boundary faces of the detailed soil. Okay. So before doing this, we need a couple of selection sets to speed up this kind of creation, because now it's quite difficult to select the faces here, okay, because they are overlapping. So first of all, what I need to do is to isolate the soil fine model, select and show, in such a way that now I can create a selection set, which actually is already here, transition slave select, okay. But if you want to create it manually, okay, you need to select all these faces, you create a new selection set, and you can call it transition slave, okay. Now, when you have everything, you switch on the visualization of everything, and you can hide. This time you can visualize only the surrounding solid. Select and visualize it. And now, well, since I deleted the previous one, you will see that transition master is empty. Select, you don't have anything. Okay, because this transition master now should have all the solids from this outer domain. Okay, so I go here. I select all the solids, select, and I create a selection set, which is already here, transition master, add to selection set. Okay. Now that I have these two selection sets, it will be very easy to create an interaction. Okay. I will show you right away how you can do it. So you go in interaction. You can call it transition. It should be a node to element. Okay. Now I need to select the master geometries, and I can simply go to the selection set and select, right click, and now I need to select the slave. I go here, select, and right click. Now the interaction is here. It is not visible, but if you switch off, okay, if you switch off the faces, you will see a preview. Okay. Now when you do the mesh, you will see the entire discretization. Now let's see how to create the mesh. You go in mesh here. You already have the mesh size, which was quite fine, which was 1 meter. Okay. But now if you use 1 meter for the entire model, you can already see here that we will have millions of elements. So it's not something that we can do now. That's why we decided to do a less accurate analysis, but the boundary elements will be, let's say, 10 times this one. In fact, even by this equation, we could use 7 or 8 as maximum size. It will not be perfect, but it should be fine. So uniform by size. Oh no, this is the global, sorry. I just need to select the sweep here. Select and show only in such a way that now I can create an edge seed uniform by size equal to 7 or 8 is the same to my entire domain. Okay, that's why I hide the structure in such a way that now it's easier to select all the edges. Assign done. Okay, now if I show everything and I build my mesh, oops, there is something that I forgot. I forgot to assign mesh controls. I want all solids to be structured and hexahedron. Assign done and build mesh. Okay, I have a mesh here. If I switch off the faces, you will see that these constraints are actually now properly placed. So every node of the slave face is connected to the nearest element. Okay, so it will move accordingly to the nearest element. Now this one is a very very strong transition. So what I did in the example that you can download, but you will be able to download on Monday, was to create a finer mesh on these 4 sides, like this edge seed, uniform by size, let's say 1/2 of that, 4 meters, or even less, let's say 2 meters. I can simply select this edge, because you will see that when you have this strong transition here, you will see very high stress concentration. So at least in these 4 sides, and also in the height, you will need a finer mesh. So I say 2, assign done, build mesh. Okay, now the transition should be smoother here. And I also need probably a better discretization on the height of this first layer. So I do the same, edge seed. I can select this one, uniform by size, 2 meters, done, and build mesh. Okay. Now if I switch off the faces, you will see the same connection, but now it's more spread. Okay. Okay, so basically once you have this interaction, you go down here, you go in the conditions, you create a new condition, which is under constraint, multi-point, ASD embedded node. And here, well, in this case, you don't have rotational dots in the solids, so you can switch off constraint rotation. You need to find a penalty value. And also here, well, there is a guideline here. It should be larger than the Young modulus of the master domain. Now, in my case, the soil was 2 to the power of 9. So also already 2 to the power of 10 should be fine. You can make it slightly larger, but not to have any numerical issues, the YAML modulus times 10 is already sufficient, because it should be at least stiffer than the soil domain. Okay, so you choose this one as a penalty value, and you assign it to the new condition. So you can go here, you select it, or you can select it from the work tree and press OK. Okay, so once you have your condition, you need to apply it. Well, since it is a staged analysis, you need to remember also something. You need to apply this transition also here. Otherwise, it will not appear in the model subset, because if you remember, you add pieces of model using the model subset, but also the constraints should be there. So when I have my where it is transition, now it is empty because I deleted the previous transition. So I select this interaction transition, and I go here in this selection set, add to selection set. Okay, why do you need that selection set? Because then here at this first stage, when you add the soil domain, you go here in edit, and before you were adding the soil domain, the whole domain, now you also need to add the transition and the absorbing element, because they are part of the soil domain. They should be there from the first stage. Okay, that's why I created a selection set also for, where is it, a selection set for the transition, but also a selection set for the absorbing element. Now you don't have them because I created once again them from the beginning, so I need to create also this selection set. So I go in sub-selection phases. I select the phases of the new absorbing element. Well, I can do it by here, or actually it's much easier if I select the material. Okay, so I have all my phases for the absorbing element, and I add them to a new selection set, which is absorbing element. Add to selection set. Okay, so now I have my where is it, soil domain that contains all the soils, the absorbing element and the transition, and so all of them will be added from the very beginning. Okay, that's why I have not only soil and whole domain, but also transition and absorbing boundary. Now from there on, everything is equal, but after this settlement analysis, okay, there was the pushover analysis, so I removed the pushover analysis. I use the activate boundary, absorbing boundary. So a simple command that you go in miscellaneous command, absorbing boundaries, ASDAbsorbingBoundary activate. You don't need to select any parameter. It's all automatic. And then I created a couple of monitors for the bottom face of the soil, the top face, so the free surface of the soil, and also a monitor on top of the structure. Okay, then I applied some damping and I set up a dynamic analysis. Now it will take a lot of time, because when you mesh this one, and here I'm using a quite coarse mesh, I tried to partition it with 6 processors, and it is more or less 13,000 elements per process. Then there is also the nonlinearity of contact, so this analysis is going to take a lot. I tried to run it, and I will show you some preview. But then I had to stop it because I was starting the webinar. Okay, but by Monday I will show you the complete model. I don't know if I will be able to send you also the output, because the output will be very heavy. Okay, but probably we can upload it. If not, we can share a link somewhere, but we will let you know. So here I have what I was trying to do this morning. For example, here for the first 0.2 seconds, it is already a couple of gigabytes. Okay, so let me go to displacement and to the initial stage. Okay, now let's see how it looks like. Now, first of all, you can see that the meshes are, let me just use this one, probably it's easier to visualize. Okay, now as you can see, the two meshes are completely attached. Okay, And this is pretty nice for connecting non-conforming meshes. Okay. Or probably it's easier if I switch off. Or let me switch on every. Let me go to the final stage. Okay, and I want to cut the model here in the middle so that you can see also the piles. So I want to hide part of this geometry and also up to here. Oh no, I need to remove the displacement, otherwise I cannot select it properly. Okay, now zero deformation. I can select. Let's see if it is fine. It should be fine. Hide. Okay, now you can see what's going on inside. Okay. Okay, now let's move back to the previous stage. And let's put some deformation. So in the first stage, you just see, oops, that's too much. The first stage, which is made only on one step, you see the gravity displacement due to the gravity of soil. Now the solution is perfectly uniform because here the hole has not been excavated yet, okay, and there is no structure, so it's pure soil. And as you can see, the solution is fine here also at the interface. Because, for example, if you remove the fissure edges, okay, you cannot see that there is another mesh here. It looks like a uniform mesh. Okay, so this is fine. The absorbing elements are acting as constraints here, as you can see here. In fact, if I go in reaction force, you should be able to see the reaction forces down here. Okay. So let's go back to the displacement. Now let's go to the second stage. In the second stage, you should be able to see the excavation. Okay, now here we have a hole. Okay, if we move from initial stage where we have the entire soil, second stage we have the excavation, so we remove the soil, and now we go back to the so we did the initial state analysis on and now off, so the displacement will be reset to 0. Okay, the displacement now reset to 0, and I apply the structure with also the beam element here. Okay, now this is actually the extrusion of the pile. Okay. No, the nodes. There it is. Okay, now I can show you. Now we have many steps here because now you have contact, so you cannot solve everything just by one step. I want to increase the deformation a little bit. And now let's move it 10 steps from now. Okay, you will see the settlement. And here you can see how nice is the transition from the very coarse mesh to the fine mesh here. It's pretty nice. So it's a nice way of embedding a detailed model into a more coarse one. And then from here, it starts the dynamic analysis, but I started only from the beginning, as you will see. And let me show everything. If I switch to acceleration. Okay, now the wave is entering here, but as you can see, it is the same Ricker wavelet. Okay, as you can see, the mesh, the critical mesh that I used using this equation has the same problem we have seen in 2D. It's too large for the Ricker wavelet. Actually, I would need 1/10 of this one, so it means more or less 1 meter, which is the same density of this mesh here. But as you can imagine, it will take a lot of time. So one thing that you can do is to use a 1 meter discretization only on the height, okay? Because now the wave is traveling vertically. So we will have a better solution, okay? But already in this case, the analysis was taking a lot. Let me see from the monitor, how long did it take just to start eating the free surface? It was just start eating the free surface, and it took it's not this one. Launch monitor. When you launch the monitor, you can visualize the time here, 1 hour and 17 minutes. And as you can see, it is not perfect. We need a finer mesh because I input a wavelet with a peak acceleration of 1 G. But as you can see here, it is slightly more than 1 G. It is 12.5. It should be 9.8. Okay. But the concept is the same. Okay. So you have the wave entering the system, which is this one, soil base. Now here it was starting eating the soil top. Okay. And then after this, you will see also the structure moving. Okay. Now I didn't have time to visualize the structure, but after the wave hits the free surface, you will see also the structure. And then the same wave going back to the bottom. Now with a slight disturbance, because now we have a structure. Instead, in the previous example, it was a pure soil domain. Okay. So now in the weekend, I will finish running this model and I will give it to you also because I have to test which is the critical mesh size in this model. And I also was not sure if this element was working well with the initial state analysis, but it seems that it is working well with the initial state analysis. So we are lucky. In the weekend, I will finish modeling, or finish running actually, this model, and I will share the result, all these files, and the new STQ version by Monday. Okay. So we are done with this webinar, and now we have a couple of minutes for questions if you have any doubt. I understand that this kind of model is quite complicated, but if you follow the steps, and probably the most important thing is the most important advice that I can give you is to use selection sets. When you have this kind of model with a lot of things that are overlapping, it's very useful to create selection set as you create your geometry, okay? Because it's very easy to go and select the pieces, okay, that you need to create, that you need for creating contact or for creating selection sets, model stages for staged analysis, and so on. Okay, so if you have any question, please.
Massimo, can I ask a question? So my question is, could you please explain again the part where you were talking about the model height, and the model height was not enough because of the wavelength of the recurve wavelet? That's the first.
Actually, I noticed it today, and I was trying to understand why, because now I need to go and look exactly at the recurve wavelet. But now the recurve wavelet, the problem is that there is an equation to compute the recurve wavelet for that frequency, but the point is that that is the predominant frequency, it's not the only one, okay? And in fact, if you compute the wavelength from the frequency divided by, from the shear wave velocity divided by the frequency, it turns out that the wavelength was about 70 meters, okay? But this was easy to visualize in 2D. But actually, you have it's slightly less. It's the total wavelength of the recurve wavelet, but you have like 3 wavelengths in there, okay? So the real wavelength that you need is much smaller. Okay, that's why I decided to divide it even more. Okay.
Okay, and the other question is, so for example, if you were going to use an earthquake input, for example, which has a variety of frequencies, then this means that we should also care about the lowest frequency that we input in the model. So then for an earthquake, to properly model one, we need a very, very, very large model because if you want to model, I don't know, very low frequencies.
But as I said, that's why I told you, when I was doing this one with the recurve wavelet, it's kind of a benchmark, so you understand what happens. Okay, it's also useful to understand what happens if you use a mesh that is larger or smaller of a certain frequency, because at the end of the day, when you apply an earthquake, first you will not be able to visualize if the solution is correct, because you have a continuous set of waves entering the system, so you will not be able to understand if everything is going well. So you need to do some benchmark before. And in this way, you can understand, you can play with it and understand if what happens, for example, if I take an earthquake and I select a range of frequency in which I'm interested, and I don't care about the others. Otherwise, I mean, you will need extremely huge models. Okay, so you need to find a compromise. Okay.
Yes. Okay. Okay. Thank you.
You selected the range of frequency that you may want to represent properly, but the point is that what happens if you do not represent properly the other frequencies? It should not be a problem, but you can use the benchmark examples in 2D to understand exactly what happens. If my mesh is too large for that frequency, is it going to create a problem, or it just dissipates some of that? Okay. So the problem is that I'm still studying this topic, so you need to use this benchmark to understand what happens. Okay.
Okay. Thanks, Massimo.
You go with the larger model, but before doing
Dennis, come on.
we don't.
Dennis has to come on. He's not coming. We have been waiting for him.
I will be there next week.
Next week, okay. It's near. Is there any other question? Some doubts?
Hey, Massimo, I'm just wondering, in your preprocessor, there's a local axis. It's for the content element, right? It's not for
The local axis, why you're talking about these ones? This one here? Yeah, this one is, I explained it in the previous webinar, is for one of the 3 contact elements, because I created 3 contact elements.
Yes.
One is for the sides of the pile. Now, fortunately, the sides of the pile have a distance between the center line of the beam and the boundary of the hole. Okay. Since there is a finite distance, I can use this option here. Compute the orientation from link direction. Okay. So when there is a distance between a master and a slave, I can compute the vector going from the master to the slave automatically in SDKO, and so you can take advantage of that. Another option was the contact for the slab, which is a node 2 element. And if you can create a node 2 element contact, I can get the orientation of the contact from the element, okay? Because I have a surface and I can compute the outward normal vector. The only problem was for the pile toe connection to the bottom of the hole, okay? In that case, the master is the node of the pile, and from just a node, I'm not able to compute the normal direction. In this case, you need a local axis, okay? So if I go on contact bottom, okay, I need to compute it in the standard way from local axis, and any local axis that you assign in OpenSees to a 0 length for contact should have the Z direction pointing from the master to the slave, okay? Otherwise, you will see compenetration. Now, the master is the soil, is the pile toe. The slave is the bottom face, so it should point downward. That's why I created a local axis pointing downward, okay? That is the only reason why I needed it.
Okay, I see. And I have other questions about when you use the absorbing boundary, have you tried to make the inner soil domain become nonlinear and like to use pressure dependent model?
I prepared the code for doing that, okay, because I was aware of this problem. And yes, for sure, when you make the inner solid nonlinear, the absorbing boundary will not work properly if you leave them as they are. But in the OpenSees code, I allowed the update of the G and Poisson ratio, the Poisson ratio of the absorbing boundary. Okay, so in the future, I will show another webinar where we can update at the end of each step the shear modulus and Poisson ratio of the absorbing boundary to match those of the nonlinear material. The only problem is that it's not going to be so easy because it's not easy to find what is the nonlinear G modulus of a material. Okay, for example, if you use a plastic model and you get the shear modulus from the tangent matrix, okay, sometimes it can be near 0. If you have softening, it can also be negative. But then when you unload, it will suddenly become the elastic G modulus, okay? So it doesn't make any sense in that case because you will have very high oscillation. So what is the G modulus of a nonlinear soil?
Yeah, and another problem is because the nonlinear soil parameter in OpenSees is all pressure dependent. So that means the G value in the free field column should also be dependent on the.
Yeah, that's why you need a way to get it from the tangent matrix. But the problem is that sometimes there you see, the entries in a tangent matrix do not always have the meaning of a stiffness. Only in the elastic case, the entries of the tangent matrix are the elastic constants. But in a nonlinear case, they are just derivatives, so they can be negative, for example. It doesn't make sense to have a negative stiffness. Okay, this is pretty much the same problem that happens if you use Rayleigh damping with the tangent stiffness. What happens when the tangent goes to 0 or is negative? Okay, it can create many problems.
But will it cause some convergence error, or maybe it just like the result doesn't?
But also on physical results. That is what I mean. Also on physical results. Because, for example, imagine the G modulus becomes negative just because it is the derivative of my stress strain law going down. I will assign a negative shear modulus to the absorbing boundaries that instead are working in a linear case. So a negative stiffness means I have a positive displacement and I have a negative force.
Mm-hmm.
And so it doesn't make sense in that case. So just to summarize, I implemented the element in such a way that I can update the shear modulus. The real problem is how do you compute the shear modulus of a nonlinear soil in such a way that it is meaningful, okay? So in my case, for example, one thing that can be meaningful would be the secant modulus. But how do you get the secant modulus from any constitutive model? So
if you start with PDNY02, it can allow you to specify the modulus reduction curve you want. So maybe that would be.
That is the reference one. The backbone curve is the reference one. But then, as you said, if you have pressure dependent, what happens? It's not that one actually. So I don't know. The problem is that it will depend on the soil model that you use. So you cannot find a unique solution. And the main problem there is how to evaluate the nonlinear G modulus, I think.
Okay. So it's just because in FLAG manual, they also mention that if your soil domain is nonlinear, you will expect some like very weird displacement along the boundary. So I think this is something they didn't like figure it out yet.
Yeah, but the nice thing is that actually I don't want to test it on this kind of absorbing boundaries because in OpenSees there is another tool that we are testing now with the professor that implemented it, which is called DRM. It stands for Domain Reduction Method, and it seems that it can solve this problem. Okay, but we are still working on it, so I don't have so much experience in that. We are testing it in this period, and in the near future we will do a webinar also on that.
Okay, thank you.
So probably with this extra tool we will be able to face this problem. Okay, any other question? Okay, so if there are no other questions, thank you for joining this webinar and see you on the next one. Okay. Bye,
Thanks,
everyone.
Massimo.
Thank you.
Thank you, Massimo.
Welcome. Bye, everyone.
Bye, UA. See you soon.
Bye, Professor.